All right, so I'm going to start with number 1. So go ahead and you can change your work if you get something wrong. Just have, your example problems ready. So you can just follow along with this. All right, the first one says how much interest accrues for a loan. Accrues just means like accumulates, or how much do you get. For a loan of $300 at an annual rate of 5% after 7 years. Oh, I should turn on the TV. Okay. So we're going to use the interest equals the principal times the rate times the time formula. We're initially investing $300. The rate we put in as a decimal. So if it's 5%, you move the decimal to the left 2 spots. So it'd be 0.05 as a decimal. That's the annual rate. So if that's per year, we need to multiply by a number of years. So we multiply by 7 years. That should come out to $105. Is that okay? Questions on that one? Okay, good. So that was number 1. Number 2 is kind of similar. It's more similar to 3. So 2 says you invest $7,500, annual rate of 3% after 21 months. So they give you months instead of years. So you're going to use the same formula. Your interest will be the 7,500 times 3%. That's 0.03. And for the number of years that you're going to multiply by, you're going to write 21 over 12. That gives you your time in years instead of months. When I tried that, I got $393.75. That good?
Yes.
Good. So this is pretty straightforward formula. You just got to make sure that if it's an annual rate, you put in years. Good.
We only put the fraction if it says in months.
Yeah.
Oh.
And if it was days, you would do per 365. That sort of thing. Then this one, if we change the wording, it says how much interest do you get if you do 15,000 at 1.6% for 45 months. So that's pretty similar. You'll do 15,000 0.016 times 45 over 12. And that should give you, I got $900 when I tried that. Any questions so far? Good. The next couple of questions ask how much is in an account after, this next one says after 8 years has passed, 2% interest, $50,000 initially invested. So 50,000 times 0.02 times 8, because it's years. That came out to be 8,000. But they want to know how much is in the account. So we're going to use that other formula where the amount is the principal plus the interest. We just found the interest. So we're going to have to add the 8,000 to the 50,000 that we initially had. So that'll be 58,000. Does that make sense? Good.
Wait, wasn't the, oh, gotcha.
We good? So number 5 is very similar. It's $15,000. We want to add that to the interest, so we're going to take $15,000 and add on the interest, which is P times R times T. That's the amount. So we will have the principal is 15,000. The rate is 0.016, and the time is 45 months. So I'm going to put 45 over 12 here. This part I got to come up to 900. So I got $15,900 as my final amount. Are we okay with that?
Is this one number 5?
Yeah. So I was doing amount equals principal plus interest. That's the formula for interest. We okay? You guys get that copied? Okay. Number 6 is now a little different. It asks for the time it would take. So how long, so I'm going to say amount equals P plus interest. The interest we know is equal to P times R times T. So they're asking, how long would it take to end up with $6,000 if we started with $5,000, and how much time would it take? So the interest would be 5,000 times, for 5%, we do 0.05 times T. Another way you could do it is just think, just thinking of I is equal to PRT. Well, if I subtract those, it's $1,000 of interest I want to make. So it's just subtracting 5,000 from both sides. Well, that doesn't fully cancel, but you get 1,000 here. And that equals PRT. So there you go. For if I initially invest $5,000, 5% interest, how long would it take to earn $1,000 in interest? That would end me up with 6,000 altogether. So to get T by itself, I just have to divide the things that are multiplying it. So I'd have to divide by 5,000 and 0.05. But in algebra, you always have to do the same thing to both sides. So that would get T by itself. And T would equal 1,000. I can cancel zeros. So it'd be 1 divided by 5 divided by 0.05. You could just do 1,000 divided by 5,000 divided by 0.05. But when you put it in your calculator, if you're doing it inline, you would want to do 1,000 divided by 5,000 divided by 0.05.
Why do you have to add 5,000 if this is 5,000 times 0.
What's that?
How come you have added 5,000, then multiplied by?
Because the amount that you have in the account is your principal plus your interest. So if you want to have $6,000, it's only going to be 1,000 in interest, but you're going to have your initial 500,000. So 5,000 plus this needs to become 1,000. You could have just started from here, just knowing that, well, to get to 6,000 from 5,000, my interest needs to be 1,000. So you can just put 1,000 there and just do the PRT part. So that should come out to approximately, I think, 4 years. Are we good? All right, on the other side, I gave you two different versions of the same formula. The left-hand side is the normal one that goes forward in time. So you start with an initial investment P, and then you multiply by a growth factor so many times based on the exponent. So it's based on the number of years and how many times you collect interest within a year. So n times t is how many times you'll multiply this thing. And the rate is attenuated based on how many times you compound in a year. R is your annual rate. So if you do it every month, you would divide your annual rate by 12 to get kind of like a monthly rate. But then you would multiply it not just once a year, but 12 times a year because you're doing it every month. On the right is a formula that goes backwards in time. So if you know how much you want to end up with, but you want to know how much you needed to put in to begin with in order to get there, you would use that other formula. It's the same thing, but with a negative exponent. The negative exponent is the same thing as dividing. So for instance, 4 divided by 2 is the same as 4 times 2 to the minus 1. So division of a regular number is the same as multiplication by a inverse power. So you could either write the second equation as the old value is the new value times that thing you took with a negative power, or you could just think of it as you're dividing. You just divided that factor to put it on the other side on the bottom. That's the same thing as having a negative exponent and multiplying. So either way you want to think of that formula on the right is fine. All right. So how much is in the account for number 7 after 4 years where 800 was initially invested at a 5% annual rate if interest compounds monthly? So I'm going to use this formula. That's my compound interest formula. So I want to know the final amount. I started with $800. I'm going to keep 100% of my initial investment, but I'm going to add on the annual rate, 0.05, divided by how many times this thing compounds in a year, which is monthly, so it happens 12 times. So that means the number of times that it happens is 12 times the number of years. I'm going to put 12 times 4 up there. this would be my function, or my formula. I plug everything in. If I do 1 plus 0.05 divided by 12, I get something like, I'm going to leave it in my calculator. I'm not going to round it now, but just so you can see, I get something like 1.00416 repeating. And I'm going to raise that to the 48th power because it's 12 times 4. So if I raise that to the 48th power, I get something like 1.220895355, blah, blah, blah. I'm going to multiply that by 800. And I get $976. And if I round up to the nearest cent, I get 72 cents. Question?
I just got the dollar on
You got what?
I just got 960.
I would go to the 2 decimal places because it's money. So you want to go smaller than a penny, right? So go to cents. Yeah. Yeah. Try not to round things like in here and or the final result when you raise it to the power. Just keep it in your calculator as it is. Your calculator keeps more digits than it shows. So I would just leave it in your calculator and then multiply by the 800. That might help. You want to save rounding to the very end. Okay, number 8, very similar. Same formula. Okay, 10 years, 9,500 was initially invested, 2.5% annual interest rate. It compounds quarterly, so it happens 4 times a year, like every 3 months. Every 3rd month. So 95,100, 1 plus 0.025 divided by 4, and 4 times 10. So on the inside of that, again, I would leave this all in your calculator, but I'm just sort of going in the order that I would put it in. I would do 1 plus 0.025 divided by 4. And I get a nice terminating decimal. And I'm going to raise it to the 40th power. Then I don't get a terminating decimal. I get something long. I got 1.283026821. I'm going to multiply that by the 9,500. And I'm going to get 12,188 and about, rounding down, 75 cents. Is that okay? The next one, I'll just leave this up. Same formula. How much is in an account after 15 years where 1,000 was initially invested at 3.2% annual interest rate, compounding monthly? So my initial amount was 1,000.
Can we use these as notes?
Yeah. We're going to do 0.032 divided by 12 for monthly. And then it's going to be 12 times 15. What is 12 times 15? 12 times 15 is 180. Right, so I will get 1,000 times 1.0026 repeating, raised to the, what do we say, 180? Times 1,000. No, I screwed something up. Oh, was this, did I do the right one? Yeah. So I got 1,615 and rounds down to 4 cents. So those each use the formula on the left. And again, I wouldn't round any of these numbers that you get here or before you get to the very end, and then you round.
So you round it up.
I rounded down in this case. It was 1615.042279. So I just went to the nearest cent. But I would round up if it was like, like 3.9, I would go to 4. Okay, this one's using the other formula. How much must be invested today at 6% annual interest to have $6,000 in 10 years if interest compounds daily? So the present amount, the principal that I'd have to invest, will equal the current amount, the amount that I'll end up with, times 1 plus the rate over n to the negative nt. So that means I'm taking the later amount and I'm dividing it over and over again. I'm not multiplying it over and over again by the gross factor. And that'll take me back to the amount that I needed to start with. It should be a smaller number, because that smaller number should grow into the bigger number of 6,000. So this represents division, not multiplication. So I'm going to have 6,000 at the end. I'm going to have 1 plus 0.06 divided by daily, so it's 365. And then my power is going to be negative 365 times the years, which is 10. So I will put that in 1 plus 0.06 divided by 365. I'm going to raise that, and I'm going to use parentheses here so that I get it all in my exponent. So I'm going to raise it to open parentheses, negative 365 times 10, close parentheses. And I ended up getting something like 0.5488387. So I get a number smaller than 1. So, because I'm going back in time. Multiply that by 6,000, and I get 3,293. And rounding down to 3 cents would mean that this would technically come up just shy of 6,000. If you wanted to overshoot 6,000, you would round up on the cent. But I would just round the cent. You can just get as close. I don't need it perfect. But this would technically come up in a couple cents under 6,000. Yeah. Yeah. Okay. The next one's very similar. So all of the same numbers pretty much, but now we're compounding quarterly, only 4 times a year instead of every day. Otherwise, it's the same. That means we should have to invest a little bit more money than we otherwise would have because we're not accumulating interest as quickly. So the old amount will be the new amount times the growth factor to the negative nt. So the later amount will be 6,000. The rate was 0.06 still. This time it's quarterly. So I'm going to divide by 4 and raise it to the 4 times 10 this time. Because there's 4 compoundings per year. Oh, I'm sorry, negative, because I'm going backwards in time. Okay, so 0.06, 1 plus 0.06 divided by 4. That's raised to the negative 40. I get approximately 0.551262322. Multiply that by 6,000. I get $3,307 and a little more than 57 cents will be needed to get to 6,000. So we needed about $14 and some cents extra because we didn't compound daily, we compounded quarterly. But it's still not too far off. Over 10 years, $14 isn't a huge deal. But we only invested 6,000. So not a huge difference there. You guys okay with that? All right, 12 is the hard one. Well, at least it involves new stuff. They want to know the time. So this is where we got to use those logs because we want to solve for the thing in the exponent. So we got to bring that exponent down, and you do that with logarithms. All right, we want to end, so I'm going to use the regular formula. Technically, either formula would work, but I'll use this formula. I want to end up with $6,000. And I'm starting with $5,000. I know the interest rate, and I know it compounds monthly. I have a 10% interest rate. It compounds monthly. So how many years would it take, t, for this equation to work out to be the same on both sides? What I'm going to start by doing is getting my my power by itself. I want to start with that. So I'm going to divide by 5,000 on both sides. Cancels here. I can cancel zeros. 6 divided by 5 is 1.2. So I get that. I got my power by itself. That's what I wanted. And now to bring this thing down, we're going to use the logarithm. So I'm going to use a natural log on the left. I'm going to use a natural log on the right. When you apply the natural logarithm on the right, the reason why we do that is it allows you to bring the exponent down in front, multiplying the log. So I'm going to end up getting Natural log of 1.2 is equal to 12 times t, and then the log, natural log of 1 plus 0.1 over 12. So the log, the reason for it is it brings the t down so that I can actually solve for it. Now, log of 1.2 is an irrational number. It's a long decimal. It is a number. Log of a number is a number. Log of this thing on the right is another number. They're just ugly numbers. They're ugly decimals. But they're numbers. You can do the same thing with them that you can do with any number. The same thing I could do with a 2. If I wanted to get t by itself, I'd divide by it. I'm going to do the same with the logs. So I'm going to divide by 12. And I'm going to divide by this log, whatever it is. But I have to do the same thing to both sides. So I'm going to divide by 12 and this other log. And that's t. So t is equal to the log of 1.2 divided by 12 divided by the log of whatever this is, 0.1 over 12. And that's how it always work out. So I'm going to say natural log of 1.2 divided by 12 divided by natural log of 1 plus 0.1 divided by 12. That gives me approximately 1.831 years. So it would take me, well, if I multiply that by 12, that's 21.97. That's about 22 months. But you just have to give it to me in years. You don't have to give it to me in months. But it works out to be pretty close to 22 months. So that's the complicated one. That's the one that involves the logs. You just apply the log. You can bring the exponent down and then divide by everything to get t by itself. That's the strategy. I'll make little notes maybe. Get power alone. That was the start. Use natural log to bring exponent down. And then isolate variable. That's how you solve for it. Any questions? All right, I would keep your example problems on your sheet and then keep that with you, look it over. Make sure you know what the question's asking. If it asks for time, you got to solve for t. If it's compound interest and it asks for time, you got to use logarithms. Otherwise, just check to see if it's asking for how much must you invest today. Is it going forward in time? Is it going backwards in time? Is it just asking for the interest, or is it asking for the value of the account? Just watch out for the wording. There you go.